98.89% more than the carbon-13, which is just 1.11.
Okay. I like where you're going. I like the data you're using. Can someone add on to that and use that to bring us to this bottom statement? Yeah, go ahead, Vasya.
With that being said, what she said with the carbon-12, with it being a higher, more natural abundance than the carbon-13, you're more likely to find carbon-12 than carbon-13 if you just gathered on the Earth a whole bunch of carbons, which you can only have two, the carbon-12 and carbon-13.
So according to this table, there's only two different types of carbon available on Earth. If we go out to more significant digits, we'll find that there are actually other forms of carbon, but not that are really abundant to any great extent. Carbon-14 exists. That's what we use for carbon dating. But it's a really, 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 really small percentage. So as far as we're concerned for today's class, there's only carbon-12 and carbon-13. If everything was carbon-12, how much would all the carbon atoms weigh? 12.000000000 AMU. If everything was carbon-13, what would the mass be? Okay, we have a number there, 13.0034 AMU for every carbon atom. So then, this number is neither of those. 12.011 is not either of those two numbers. So then, what do we describe that number at the bottom as from your homework, Sam?
It's the average.
It's the average of 12 and 13. Shouldn't that be 12.5?
Well, the average of 98% 12 and 1% 13.
It's the weighted average. That's great. Okay, so today's class we're going to be focusing on that number at the bottom of the periodic table. A lot of people over the last 2 weeks wanted to use as the mass of an individual isotope is not the mass of any one isotope. It tells you, if you have multiple isotopes, well, which one do you have more of? The heavier one or the lighter one? Is it closer to the lighter number or the heavier number? And so we know both from this table that we have 98.89% of carbon-12. But we also know from this, if we're only looking for carbon-12 and carbon-13, that number is so close to carbon-12 that's basically saying that we almost only have carbon-12, and then there might be a little bit of something heavier, the carbon-13. All right, so I completely agree with your second set of answers. That is an overwhelming majority of carbon-12. And then we're going to be spending some more time in the packet with that. Olivia, can I grab your computer and show one thing?
Yes.
Thank you. Some of you noticed that there was a dynamic module last night.
Yeah.
Homework module. That was a set of practice problems. Let's see if I can do this. Quite sure something happens like that.
Yes, it's some bad things to that one. I like having.
So I received a number of emails about it, some positive, some confused. But what I wanted to show you is that you have a large number of dynamic study modules available to you at all times throughout the semester. I decided to make one assigned. It was for practice, it wasn't for credit, so that you would see it and you would know that you have a lot more practice opportunities available. So this is your homepage for the course. Did you guys see this before? Okay, so if you want, you can click on that. It brings you into a specific part of the Mastering in Chemistry, and then you can select what portion of that you want to use in order to study and practice. If you want math skills, dimensional analysis, scientific notation, unit conversion, all that kind of stuff, that's in here. General chemistry.
Did you click under a certain chapter for that?
There's no chapter. That's the first page you get to is this.
Okay.
So if you want to do the math skills, you would click on the math skills. You can do those skills. If instead you want to do, so this is the one that I assigned, was atomic structure. You can go back in, even if you didn't do it before the assigned deadline, because it's not really a deadline, it's for practice. Periodic trends, we're not going to probably spend as much time with some of these. But if for this next exam you want to look at electron configuration, we're going to spend a decent amount of time with that. You can click on that, and then it gets into the stuff that we're going to be starting in class on Wednesday. Okay? So I just wanted to point out that there is an amazing resource available that you can utilize. And one other thing I want to make sure that you are aware of is when you're inside of a problem, does everyone know how to get to your book? So if you're inside of a problem, if you click on the little review button, oops, I right-clicked.
You gotta have the book though.
If you got the digital platform as a whole, then you click on this link right here, and it'll take you to the ebook for the section for that question. So that's why the pre-class quiz, even if you don't have the book, it should still pop up with that, but it might just say that you're not allowed to get to the website. It should still tell you what chapter of the book you need to go to. So if it's 2.7, 2.8, that should be true for the older versions of the book. Like I said at the very beginning of class, I do highly recommend having some version of the book. If you want to go buy the 7th or the 8th edition online, used, or something like that, that's cool. You'll probably find for $20 for the 7th edition, whatever you can find. This is going to be a way to help you kind of get there and to navigate that. Any questions on those logistics?
I actually have a question. What do we need to have read by Wednesday? Do we need to start chapter 3 or just?
So class on Wednesday, the pre-class quiz is up, and it is about electron configurations. So make sure you can go through that. I think it's chapters 2.6 and 2.7.
So we haven't yet entered chapter 3.
No, we have not gone to chapter 3. And we will barely before exam 3. I think we'll get to that on Monday. All right, we have been running again. Still recording. Okay. So my objectives for you all today is by the end of today's class, you'll be able to utilize logic to determine the relative abundance of different isotopes for any particular element. Yes, we can calculate all this. There are formulas, but I want you to be able to look at a number and say, oh, because of that number at the bottom of the periodic table, I know that this isotope is more abundant than the other one. And then we're also going to be able to calculate the average mass if we know the different isotopes that are available. I think that's it. It's pretty simple, right? Can we do this? We can totally do this. Talking about the exam and study tools, would you like to have a topic guide to help study from?
Yes.
Done.
Thank you.
Every class I give you parts of it. No, I'm not kidding. This is what I want you to be able to do, and not just electron configuration or isotopic mass, right? That's not really useful to you, giving you a list of topics. I'm telling you, within that discipline, you need to be able to calculate the average mass from having the relative abundance, not the other way around, okay? So it's very specific about what you need to be able to do with that. All of my slides are posted to Blackboard content, so go there, pull those out, make your own study guide from that, and anything else that we hand out in class. I do not generate a combined list of these. I think that it is important that you do that yourself, and that you use these to go check maybe a day or two after class, go back and look, say, can I do this? Let me try doing some problems, make sure I can do this. And the homework should align with that, and the activities we have in class. Be bad if there's another one now, wouldn't it? All right, let's make sure we're all on the same page of reading this table. Using that first table, how many isotopes of magnesium are there naturally occurring on Earth? It's a clicker question. Josh, just in time. Can you set your bag down? Give me a hand. And a Kia as well, since you're available. Sarah, if you want. The same location services drop, or?
No, I turned them on, it said I'm not in the right location.
Yeah, my clicker just logged me out too.
What does it say?
It's saying I'm not in class.
Location. You're on Wi-Fi? Okay, I'll turn.
Do we have to be on Wi-Fi? Whoops. Is that helpful? What's the Wi-Fi?
If you do not connect, if a iClicker says you're not in class, then join the UALR Wi-Fi. It'll help. Are you on guest network? Okay. Give me a second after the next question. I'll turn it off for location services, and you can retry, okay? I'm giving you one of the coolest things you'll get all semester, in or out of class.
Ever in life. Ever.
You know what'd be cooler? An A.
Turns out you're the only one that can give yourself that. All right, couple more seconds.
Woo, you little more. What's the question?
Question is at the top of the screen. I'm not sure why it's... All right. Just want to make sure we can read the table. Closing out. We have 6 more people who haven't responded. Come on, help out. All right, try logging in now. Eleanor, try logging in now. Or you already joined? You good? Connected? Yes, no? Yes? Are you connected? Okay. All right. 52 responses. All right. Just want to make sure that we're looking at this table and we're all agreeing. With magnesium, we have 3 different isotopes. What's the difference between each one of these isotopes? Can I get a hand raised? A new voice. Carmen?
The neutrons.
Say more about it. The neutrons is...
The weight.
Okay, so maybe what's similar, what's different? Give me a little more than a single word, please.
Gosh, okay, I shouldn't raise my hand.
No, it's all good. You know what you're saying, you just need to verbalize it so everyone in the room knows what you're saying.
The neutrons have different masses. No, I don't know. Man. I mean, I don't know how to explain. I just know. You know it.
Can someone else help out?
There you go.
Clarify the statement. Dustin, I see you raising your hand. Can you explain the difference between the 3?
As you go up, it adds 1 neutron.
Okay, so what's the same between all the magnesiums and what's different between them?
They all have the same number of protons, but they have different numbers of neutrons.
Fantastic. That's it. So isotope just means it's the same element, but it has a different number of neutrons. So with that, we're answering questions 1 and 2. All right. Go ahead and write down your notes if you need to. And then we are going to do a clicker basically for what question 3 is.
What is guidance?
Process-oriented, guided the approach to basically focus on the process instead of the answer. Always. All right, I have 33 responses. Basically, try to answer question 3, which is asking you something on, I think the same exact question as this. Read carefully. Couple more seconds. Looks like we got almost everybody in. Closing out. Volunteer. What did you answer and why? The room is very quiet today.
I'd raise my hand for everything if I could.
Ryan? What did you answer?
12,
Why?
because you're more likely to get 12 than you are 13.
Fantastic. Why are you not going to find 12.01?
That's the way it's told.
Great. So you're either going to find this one, or you're going to find that one. You're not going to find the average of those. Great. All right, go ahead and make sure to answer question 4. And what approach might I want you to use to answer this question? Yes. Show dimensional analysis how you'd answer questions 4A and B, please.
I don't know. Who would go there? Just to say like, how many?
Is there anyone else who doesn't have a packet?
You just see if okay, I haven't done this. I didn't know what the dimensional analysis teach me like 1,000 of those. How much does it weigh? So what do you ask? That's it. You know, write it out the dimension.
No, to write it out like dimensional analysis. What's your starting quantity? What's your conversion factor? What's your and then theoretically you could say, well, if I asked you for grams, you could do that.
We would need that conversion factor.
I think that's where it's like the wording. It says M-A-N. What do we need? So, what is the salary?
What could you do to be a little bit more specific? Sweet. You know what I'm asking for? Do you know what I'm asking for here?
Are you talking about the long way?
Mm-hmm. My long way.
Those.
So how do you write this out in unit conversion approach? A little bit more specific. What is that? You're at 12.00? Okay. So you're almost there, but I think, can you expand on what that squiggle is and that squiggle is?
So what you're doing is
So let's make sure that we're all doing this the same way. On the exam, I will have questions like this, and I will want you to show your work. So I do need you to show all the steps. What is our starting quantity for it?
I started differently.
And then what conversion factor do we have to go from the number of them to how heavy they are? 12 AMU over every carbon-12 atom weighs 12 AMU. Or if we have 12 AMU of carbon-12, then that's one carbon atom. So if we do that, we end up with an answer of 12,000 AMU. Is that what you did logically right from the start?
Yeah.
But did you show it this way? Some people did, some people didn't. What's different about carbon-13, 1,000 carbon-13 atoms? What would we change about this? Lena? So the only thing we change would be this? Okay, our starting quantity is different, right? We have 1,000 carbon-13 atoms. And we know that every carbon-13 atom weighs how much? 13.00, what is it? So then our answer is that right? Do I have one extra zero in there? Or is that right?
That's right.
Okay. So for this question, because we're using an exact number, should be an exact number, how would we make sure that we know that this is an exact number of the 1,000? How do we do that with sig figs? How do we show what this 1,000 is exactly 1,000, not 1,001, not 999? We just put a decimal after it. And that tells us exactly. If we do 0.0, that means there could be a fraction of a carbon atom, and there can't. So that's the other thing. It's like saying, how many eggs do we have? We can't have a fraction of an egg, so really this is going to be an exact number anyway. So this is an exact number. It's like saying we have 3 eggs. How much do they weigh? This is a number that we can look up that's much more precise. So honestly, we could write out more sig figs, but both of these are precise, and so you want to try to keep it to however many are in the problem that you're given. This is not a great question for sig figs because none of these numbers are a measured value that has uncertainty in it. There's no uncertainty at 1,000 carbon-13 atoms. That's exactly 1,000 of them. If it was about 500 or about 17,000, then maybe we'd have some uncertainty we have to work with. All right. So then what about our next question? Go ahead and flip the page. I think I might have this as a clicker question.
I don't know.
So see which one of those answers makes most sense for question 5, and then basically answer a similar question here.
Do you want me to write the value, or do you want to start the letter? Question 5, it's A, B, C, D, E.
Right, it's numeric response. So you can't do a letter. I think. Let's do multiple choice.
Yay!
It's like, I didn't think I animated that. I did. That was a bad idea. Sorry, same question. Multiple choice. Talk to your neighbor. See if you agree with them. And then once you've done that, go ahead and calculate to see exactly what it would be. All right, I'm going to go ahead and close out. All right, can I have a new voice? Someone from this back corner of the room. Share what answer you chose and why, and then maybe a second person to say how we'd actually calculate it, similar to what we just did with the other two. Anybody? Why does no one bring their name tents anymore? Do you expect me to learn your names in 4 class periods?
Yep.
Sorry.
Yes.
Thank you, Robert. I appreciate you pulling it. I saw your name tent there. Pull it out. You're one of the few I remember. That means you don't have to answer this question. Please volunteer. Which answer did you choose and why, logically? Great, thanks.
Okay, I selected B because if you were choosing carbon at random, you could possibly get the carbon, or 13 carbon, which has a little bit more carbon.
Fantastic. So if we look back at the last set of calculations that we did, here are those calculations. And if we had all carbon 12s, it'd be 12,000 AMU. If we had all carbon 13s, it'd be 13,000 AMU. We know that this is not really very likely to happen, but it's going to happen some percent of the time, 1% of the time, right? So every few, we're going to get a few carbon 13s by the end, which means that the mass, could it be lower than 12,000 AMU? If we have 1,000 carbon atoms, there's no way that that can weigh any less than 12,000 AMU total. So it can't be less than 12,000. It can't be more than 13,000. That's really important when you do your calculations. I guarantee you sometimes you're going to get a wonky number that's not going to make any sense, but you're just going to be focused on the math and you're going to forget about it. So always go check, what should my limit be? What should my minimum be? What should my maximum be? It's got to be between those, and then it's going to be really close to this number because almost every single one that we pull is going to be this carbon 12. Okay? And then how would we show that in a calculation? What would be the same? What would be different about these calculations? We would find the actual value.
You would do the average.
What do you mean we do the average?
So, like, for your conversion factor, you would put an average carbon atom over 12.01 AMU. Because that's what the average weight is for carbon.
Great. So we would change two small things. We would say carbon atoms. This implies that it's the natural abundance on Earth. If we're astronauts and we're going to Mars, okay, then we're going to have a different conversation about this, but for now, we're assuming everything happens on Earth, and the natural abundance that we have on this page, and what dictates what's on the periodic table is what we're using. So they're all carbon 12, or carbon atoms, not carbon 13 or 12, we don't specify that, which then means we have to use the weighted average for every carbon atom. Does that mean if we go in that pile and we pluck a carbon, we're going to find a carbon that weighs 12.011 AMU? Okay, just because it's an average values between the two doesn't mean we're going to find anything that weighs that. All right. Thank you for those great explanations. Let's go ahead now and read the beginning of Model 2 if you have not already. Read it very carefully and look at the two different equations that they use. Once you've read through it, there's two equations, and then we're going to start answering some questions. All right, go ahead and put in your answer to question number 6. Y'all don't need to be so quiet. You can talk to other people. So answer question number 6 by clicker, and then keep working. Come back together and talk about it. If you're not getting what they're asking, or you're a little bit confused, just raise your hand. We have plenty of people to help today. Try to make sure your responses are clicked in. Closing out, submit your response, submit it, submit it, submit it. All right, new volunteer, what's your answer? Great. Why 0? There's 4 on the scale. Say again?
3.
Hold on, let's follow up with your answer. Why? Yeah. Okay, so all 3 of the dark ones are 7 grams. The white one is 5 grams, and so none of those weigh 6.5 grams. So then what is the 6.5? All right. So I know that we said this in the beginning of class, and we keep coming back to this, but it is really difficult to kind of wrap your head around this. That number on the periodic table doesn't tell you about any particular isotope. It tells you about a weighted average. It's like if you had a GPA of 3.6 at Euler, actually anywhere, could you get a 3.6 in any one class? 3.6 GPA. So a GPA is another example of a weighted average. You cannot get a 3.6. Certain schools you can't get an A plus or A minus or a B plus, and you can get like a 3.0 or a 2.0 or a 2.3 or whatever it is. But you can't get something that's in between those, so your GPA that you show on your transcript is always going to be a weighted average. Same exact thing applies here. There's 2 different ways you can do that. Right? Equation 1, which says that you have a total of 4 of them. 1 of them is 5, and then you're adding that to 3 of them that are 7 grams. And the average of all those masses is 6.50 grams. What did they do in the second one that's different? Second approach. You don't need to know the total number. What do you need to know instead? You need to know the percentage, or more specifically, the fraction, the decimal form of the percentage of how many of each there are. So if you're not super comfortable with decimals, once again, this is going to be somewhere to point that out. That 25%, 0.250. If you're not comfortable with that, make sure to practice or see me in office hours or the Math Assistance Center. 0.75 is 75%, and so you can multiply those and find the weighted average. So the next question, question number 7, asks you then to apply that to a scenario using the second equation, using the percentages or the decimal form of your percentages to figure out what the weighted average is for that next set of compounds. So the answer to that one, we absolutely agree with the people that spoke up, was there are 0 that weigh the average. Okay? So let's go ahead and answer question number 8. Question number 8 is based off of question number 7. So make sure to read question 7 and then answer question 8. Is it? Nope, I lied. Sorry. Question number 8 has nothing to do with question number 7. Question number 8 has something to do with question number 8.
You have to use
Plenty on
method,
our own
you have to
things.
use method 2, so like it kind of.
Let me see. All right. I totally just confusing the heck out of you guys. Let's actually answer question number 7, not the method. All right, does everyone know what we're getting at now? We're answering question 7 because it is probably useful to see how we answer that. Question number 7, mathematically answered. Finish question 7, keep going. There's a lot more time. All right, we have 34 responses to question 7. Make sure to click in your response. We'll go over it in a minute. But keep working as you finish question 7. Go into question 8. Back.
I got the same. That's in my transfer.
calculation everywhere? Basically, this. Think about sig figs.
You already have the average. That's what the equation helps you calculate. Think about that number if it makes sense. Is this number going to be the average weight if marble is the weight either that or that?
Yeah, no.
All right, 45 responses.
Oh, we can't change that answer.
So before we do any calculations or talk about anything, what's the first thing we should do before we calculate anything and put it in our calculator?
Make sure it makes sense.
Think about what makes sense. So for this particular problem, if we have marble as the weight 10, we have marble as the weight 12. It doesn't matter how many of each we have, what's the extreme range that we could have for the average weight? Between 10 and 12. If we get a number outside of that, then we know that we messed up somewhere and we need to go back and look at what equation we used or whatever else we did. Okay? So if we're trying to do this problem, what would we do mathematically? Someone walk me through what they did. Monica, do you want to describe what you did?
I did 37.2 times 100. And came up with a number and multiplied it by 10.0.
Why are you multiplying 37.2 by 100? Where's that coming from?
Because of to get the percent.
Oh, you mean divided by. So you were going from percentage to decimal form. So let's just go ahead for now. We're going to write out 0.372. Because everything when we have in decimal form is always going to be less than 1. So if we ever have multiplication, something ends up really big, then that's going to be a sign. Okay? So 0.372 is 37.2%. We're going to multiply that by 10.0. Let's throw units in there. And then?
And then I did the same on the other side. I did 62.8 times the 100
Divided by?
to get the 0.6288. And I multiplied that by 12.00. And then I added both of those together.
Okay. And so I want you to try to do them together because sometimes we might have 3 different marbles, right? 3 different isotopes. And then we could do them all in a row and put them all together. So if we do these calculations, what happens if we just plug this in our calculator without any parentheses? Does that work? I think that might, I can't remember if that gives you a problem this one or not. Parentheses, multiplication.
It did with me.
I think it would be fine with this one.
No, I had a little problem. I had to redo it.
Okay. But that's going to be one of the most common problems you have is your order of operations. So in chemistry as a whole, make sure that you put parentheses around calculations you know should be together. So if you're thinking about doing it in multiple steps, but you want to combine the steps, put parentheses around the steps you're going to do separate. So if we do that, what value did you come up with?
11.256.
Units? Okay, maybe I didn't hear you, sorry. Great. Perfect answer? We got to pay attention to sig figs in this one. If someone went out and measured, marble weighs 12.00 grams. That means that we only know to the hundredths place. Same with the other marble. So how are we going to limit our answer here? Over here on the left side, we're going to limit our answer to the tenths place. Well, no, 3 sig figs, sorry. So we have 3 sig figs, 3 sig figs. We're using multiplication rules. Over here we have 3 sig figs and 4 sig figs, so we can limit that to 4 sig figs. And then this, I don't know what the actual value is. What is the actual value of these two sides? 3.72. Okay. And then we take these two and add those together based off of their sig figs. We would take whatever number the calculator spit out here, and we would add that to it. But based on this, we can see that this one, now we're doing addition rules. So this is at the hundredths place. This one has certainty at the thousandths place, so this one has least significance, certainty, so that we would limit our answer to the hundredths place. All right? It's really important that you do order of operations here too. We're doing this calculation first. What should the answer be limited to sig figs? We're doing this operation. What's the answer limited to sig figs? And then the next operation has a different set of sig fig rules. So we have to do that afterwards. So what is our final answer? Is this the right answer? Is that limiting it to the hundredths place? Nope. $11.26 is the right answer. This is one of the more complicated problems because you have to think about the two different sets of sig fig rules separately and then combining them. If you just put in your calculator, you're like, 3 sig figs limits, then you're ignoring the fact that you have addition subtraction rules and that's a different set of rules. That's based off of the second decimal place, the hundredths place, is certain here. And this one has certainty there and one past it. We always use the weakest, the least accurate value to limit our answer. So 11.26 would be our final answer. Questions? Yes? Correct. So the first one, we say how many significant figures, like regular rules. But then we say, okay, these are our final answers. This one has less certainty at the decimal places than this one, so that's what we limit our answer to, because it's now addition rules.
So if, for example, the first one had 7, 2, 1 after it, we would do 3 after it.
If we had 4 sig figs in both of these.
No, I mean in the addition part where it says 3.72.
Right, but I'm saying if these each had 4 sig figs, if this was 10.00 grams and 0.3721 or something like that, this had one more digit, then we would limit it, we would put it at 6. 256 is the answer. Honestly, this is one of the sets of rules that you just really want to learn at the beginning of the semester. Every single exam, every single lab report, you will get dinged for not knowing this, and I can't even tell you how many students just be like, I'm just not going to worry about it. And at the end of the semester, they've lost, a full percentage point of the semester because they just never once learned at the beginning. Kalia, is that you saying, I agree? That was you? Okay, so Kalia was in our class last spring, and that was her.
Okay.
All right, so let's go ahead and continue on our next page. Let me see how many people actually got that. We got 46%. I don't know how I left it open at the end, but good job, guys. All right, so let's go ahead and do question 8 and keep working on the back side. We're now going to make sure that we can work through these types of problems with isotopes instead of with marbles, but the same principles apply. So think about how to use the approach we just did. In this one, are we going to use sig figs? I mean, these numbers are not someone went out and measured this. These are all very accurate numbers. So there's no real limiting sig figs here, I don't think. The questions 8 and 9, just limit it to a good number of sig figs that kind of matches what we have on the table.
Oh my god. Are we stupid? Are we looking for it's not saying. We don't lock it up.
It's good to keep them long. When you do your calculations, yes, keep them long to your calculations. And to make sure that you do
Yeah, in this syllabus I have yeah, that works. I need to check there is the particle policy by the graphic calculator when I'm trying to provide it. Okay, so if you had a choice to get one from scratch right now, it doesn't have to be paid. Okay. That's the kind that you recommend. Make sure you I mean, you can also just use exponential. Most of exponentials give that but sometimes it misses.
And when you add
I'm just asking you is that a number? How do you check? I'm just saying all of this. You check to see what's true. Think about that. All right, let's go through and answer some of these questions. Hopefully you're starting to gain a little bit of comfort and momentum with this. So if we use the equation 2 to calculate the average mass, why can't we use equation 1 to answer question 8a? We don't know how many of them there are, right? It's not like there are 4 chlorine atoms. We have any amount of chlorine atoms. We're really talking about the abundance. So if we do that equation, then what do we find to be the average atomic mass in AMU? Olivia?
35.452780.
Does that number make sense? Okay, so sig figs are a little bit mushy here because all of these are very precise values. So it's not like someone went out and weighed 10.0 grams like that last problem of marbles. This is, if you can picture where these values come from, the percent abundance on Earth means that scientists have gone out and measured around the world and congregated millions of data points. So we can probably go look up much more accurate versions of these numbers, and so we kind of call these exact numbers. So if we're using two exact numbers, then, so I saw some people rounding it off to 4 sig figs, which is fine. Some people rounded it off to a little bit more. I don't really care with these ones. The time when it does matter about sig figs is if there is a measured value that had uncertainty in it, and maintaining that uncertainty in your answer, recording that uncertainty. So the question I had is, and we probably should have done this before we did the calculation, what range should this answer be in?
34.
Between 34 and 36?
Or 35 and 37.
Okay, so we're between 35 and 37. Okay, it could be slightly below 35 because the actual mass of chlorine 35 is, what is it, 34.9689. But it shouldn't be 34. If we say 34 and higher, that means that we're saying that 34.5 could be an okay number for this. It is not. Okay, so it has to be between the mass of the two isotopes. And check our answer afterwards. 35.453 is what that periodic table has. I don't know what it is on the one you have in your periodic table card I gave you. It's somewhere fairly close, right? All right, big question then. What fraction or percentage of chlorine atoms weigh that much? Catching on? None of them weigh the average. All right. So if we, for question 9, for a large collection of randomly selected chlorine atoms, what is the average atomic mass in AMU? Where do we find that number? Periodic table, we don't need to calculate it. Someone's already done that for us for every single isotope. Okay? What it's having you do is it's having you practice how they found that number. It's not going to say you have to do that every time. You are going to have to prove to me in exam 1 that you know how to find that weighted average. And I might throw a curveball question in there and say, here are some isotopes found on Mars. What is the weighted average? It might not match what's on the periodic table. Okay? These are the abundances for Earth. So I want to see if you have the process down and you can figure out the right answer, the right value. What is the average mass of a chlorine atom in grams? How do we answer that question? Dimensional analysis, unit conversion approach. What's our starting quantity? Go ahead and do that problem if you haven't already. Go ahead and answer question 9b. Write it out. Let me see how you would find that. And then question 10 is a follow-up to that. And if you finish those, keep going, answer lots more questions. All right, we're going to walk through this question relatively briefly, and then I have a speed round of a couple questions to see if you can do that logic part. In this question 9b, what is our starting quantity? Can you read the question? I didn't hear 35 in that question at all. What's the starting quantity in that question? Sorry, green is probably a terrible color. So I think most of the class did what you did. And they started with, well, I know one chlorine atom weighs this much, so you just start there. But that's not what the question's asking. The question is saying, how much does one chlorine atom weigh? That's your starting quantity. We always start there. Don't skip steps. Show every step, please. So then if we know that one chlorine atom is our starting quantity, we're not specifying the isotope, right? Because it's an average chlorine atom. Then what is our conversion factor? How do we take what you just said and make it a conversion factor? Take a shot, or you want to pass? 35 point, what was it? AMU over 1 what? Great. That's the conversion factor you found in 8a. So now we know that chlorine atom, we know exactly how much it weighs, and now we can change the quantity of chlorine atoms. If we had 17 chlorine atoms, we could still use the same approach, the same setup. And then we know that we want this answer, if we wanted an AMU, we stop. What if we want the answer in grams? Not quite. It's a version of Avogadro's number, but we know that 1 AMU times 10 negative 24th grams, and that's how we can convert from AMU to grams. I will give you that last conversion factor on the exam. There's no reason you need to memorize that, but it's something you might memorize anyway because you're using it so much. What? I will give that last conversion factor on the exam. Okay, and is it going to be a big or small number? Super small number. Next question is different because this starting quantity is 6.022 times 10 to the 23rd, right? Did anyone figure out what that answer is? Avogadro's number of chlorine atoms weighs 35.453 grams. Does that number look familiar? Okay, so we're going to be playing with that throughout the semester. Lightning round of questions. Ready? Lightning round of questions, and go. Two major isotopes of bromine are 79 and 81. Assume that for right now that the masses are as shown there. What would you guess the approximate relative abundance of those two isotopes is? Don't pull out your calculator.
Some of us were having, it was set idle for too long, so we had to go back and log back in.
Okay. So is this an easy question? How are we approaching this? What information do we need? I see a lot of people pointing the periodic table. You have your own now too, right? What number's on there that's really going to be helpful? The weighted atomic average is there for you. What do we see as the weighted atomic average for bromine? 79.904. So, is there going to be, does this answer A make sense? What's wrong with this answer A? It has to be 100% total. You can't have more than 100% total. Okay? But they're like 79, that looks great. I love it. 50-50. What do you think? Are we close to about 50-50? What would the mass be if it was a 50-50 mixture? It would be right in the middle at 80. But this is way too far towards the light one, way too far towards the heavy one. So this question is basically saying that we're going to just look at that number and say, you know, it's pretty close to right in the middle. So I would estimate, right, we're estimating, we're being really rough in our estimations here, that it's about an equal mixture of the two. Which one is there more of, the lighter one or the heavier one? There's more of the lighter one because the average is slightly closer to the lighter one. All right, you have homework that's going to help you practice this. You have a dynamic study module, I think, that might have some of this in it. And I will see you class on Wednesday. What do you have to do before Wednesday? Homework 3 is due tomorrow night. Post quiz is due Wednesday night. There's a pre-class quiz for Wednesday. So if you haven't been on it, homework 3 shouldn't take too long. But hopefully after today's class you can do it, no problem. Are they what? No, it's practice 3.